Hello everyone, I'm Dr. Eris, and I'm thrilled to begin our session on the mathematical foundations of artificial intelligence. Today, we're exploring why linear algebra is truly the engine that powers modern AI. First, we look at data representation. Whether it's a digital photo, a block of text, or a voice recording, AI doesn't see them as we do. Everything is encoded into vectors and matrices, creating a numerical grid that algorithms can actually process and learn from. But why has AI exploded recently? The answer lies in computational power. GPU acceleration is essentially just massive, parallel matrix multiplication. Linear algebra allows us to perform billions of calculations simultaneously, which is what makes training deep neural networks possible. Our roadmap for this session is ambitious. We'll start with the atoms of data vectors and move through matrix operations until we reach singular value decomposition, a powerful tool used in everything from recommendation systems to image compression. Building on the overview we just covered, let's dive into the fundamental building blocks of AI, vectors. We often call them the atoms of data, because every complex structure we'll study today, from the grids of information in matrices to the high-dimensional tensors, is ultimately composed of these units. At its core, a vector is an entity defined by both magnitude and direction. While physicists might think of them as arrows, as AI developers, we treat them as ordered lists of numbers that represent specific features of our data. Mathematically, we represent this as a column, where each entry x corresponds to a value along a specific axis. This notation is what allows our computers to perform thousands of operations simultaneously. To visualize this, look at the scatter plot. Here, we see vectors in a 2D space. Each point is a vector originating from the origin. Understanding this geometric interpretation is vital because when we talk about data similarity in machine learning, we are essentially measuring the distance or the angle between these vectors in n-dimensional space. Finally, we have the practical application, feature engineering. By using vector addition and scalar multiplication, we can transform, scale, and combine raw data into meaningful inputs for our models. Now that we've seen the atoms, let's see what happens when we stack them together into matrices. Building on the vectors we just covered, think of a matrix as a structured grid of information. It's essentially a collection of vectors stacked together, forming the primary structure used to store and process datasets in AI. To work effectively with these grids, we must understand their anatomy. We describe a matrix by its dimensions, denoted as m by n. In our field, rows usually represent individual samples or data points, while columns represent the specific features of those samples. This standard mapping is what allows algorithms to process thousands of inputs simultaneously. Look at this 3x3 identity matrix. It has ones along the main diagonal and zeros everywhere else. Much like the number 1 in basic multiplication, the identity matrix is a neutral element that becomes vital when we discuss matrix inverses later in the session. Compare that to a typical 3x2 data matrix shown here. This could represent 3 different images, each with 2 pixel values, or 3 students with 2 test scores. The matrix structure keeps this data organized for computation. Lastly, we have the transpose operation, denoted by a capital T. It simply flips the matrix over its diagonal, turning rows into columns. We use this constantly to ensure that 2 matrices have matching dimensions before we try to multiply them. Building on the matrix shapes and transposes we just covered, let's dive into the actual mechanics of how these grids interact through multiplication. The fundamental operation at play here is the dot product. In the world of AI, you can think of this as a similarity check. It measures how well an input vector aligns with the patterns the network is looking for. This also acts as a mapping process. By treating matrix multiplication as a series of linear combinations, we effectively transform our data from one coordinate system to another, extracting higher-level features as we go. Now, recall the importance of matching dimensions from our previous page. For multiplication to be mathematically valid, the inner dimensions represented by n here must be identical. The resulting matrix will then inherit the outer dimensions m and p. To see why this matters for your code, look at this single neuron output formula. That summation is exactly the dot product of weights and inputs. When we scale this up to thousands of neurons, matrix multiplication becomes the engine that makes deep learning possible. Take a look at this visual representation. It shows the flow of data through those weighted sums we just described. In this simulation, we will explore how a 2x2 matrix transforms 2D space and the unit square. These sliders control the entries of the matrix. Each column determines where the basis vectors 1, 0, and 0, 1 land. By increasing the diagonal elements to 2, we have scaled the space. Notice how the area of the square is now 4 times larger. Matrices can also rotate space. Here, the unit square has been rotated 45 degrees without changing its area. Changing the off-diagonal elements creates a shear transformation, tilting the square while keeping its base on the x-axis. When the determinant is 0, the matrix is singular. Watch how the 2D space collapses into a single line, losing a dimension. Experiment with different values to see how the determinant, the area scaling factor, changes based on these transformations. Building on the identity matrix we just covered, let's explore how to undo transformations. In linear algebra, this is the core of solving systems of equations, which is essentially what we do when we train a model to find weights. The concept of an inverse, A inverse, is defined by this relationship. When you multiply a matrix by its inverse, you return to the identity matrix. Think of it as the reciprocal of a number, but for grids of data. This is mathematically critical for solving AX equals B. By multiplying both sides by the inverse of A, we isolate X. In the context of AI, X often represents the weights we are trying to learn from our features, A to predict B. However, we hit a wall if the matrix is singular, meaning its determinant is 0. This usually happens when our data features are linearly dependent or redundant. You can't invert a matrix that doesn't provide enough independent information. To handle these real-world messy datasets, we use the Moore-Penrose pseudo-inverse. It allows us to find a best-fit solution even when a perfect inverse doesn't exist, which is the secret sauce behind many regression algorithms. Building on our discussion of finding the best-fit solution, we need a way to quantify how far our predictions are from the actual values. This is where vector norms come in. They are the mathematical rulers we use to measure the length or magnitude of error vectors. The most common measure is the L2 norm, often called the Euclidean distance. It represents the straight-line distance from the origin to the point in space. Notice the formula. We square each component, sum them, and take the square root. Because we square the errors, large outliers are penalized much more heavily than small ones. This is the mathematical engine behind ridge regularization, providing stability to our models. In contrast, the L1 norm, or Manhattan distance, measures distance as if you were navigating a grid of city streets. Here, we simply sum the absolute values of the components. This subtle change creates sparsity in our data. In lasso regularization, L1 actually forces the coefficients of less important features to become exactly 0, effectively performing feature selection. Take a look at this visual comparison. The L2 unit circle is smooth, while the L1 circle is a diamond. Those sharp corners on the axes are precisely where the L1 norm hits 0 for certain dimensions, which is why it's so good at simplifying complex models. To wrap up this concept, think of lasso and L1 for selection and simplicity, and ridge and L2 for stability and handling large errors. Before we move on to eigenvalues, let's think about how these might behave in a high-dimensional space. Building on what we just covered regarding vector norms and high-dimensional space, we now reach one of the most critical concepts in linear algebra for AI: eigenvalues and eigenvectors. This formula is our fundamental definition. It tells us that for a specific matrix A, there exist special vectors V that, when multiplied by A, don't change their orientation, they are simply scaled by a value lambda. This lambda is our eigenvalue. Think of these as invariant directions. While most vectors get knocked around and rotated during a transformation, eigenvectors stay on their original line. They define the skeleton of the transformation. Let's take a look at this visually. Pay close attention to the vectors that only stretch or shrink without flipping or rotating as the transformation occurs. This isn't just abstract math. In principal component analysis, or PCA, we use this eigendecomposition to find the principal axes of data spread. This allows us to compress massive datasets by focusing only on the directions with the most information. Building directly on our exploration of eigenvalues, we arrive at the singular value decomposition, or SVD. While we just covered how eigendecomposition works for square matrices, SVD is the Swiss Army knife, because it can decompose any matrix, regardless of its shape. The fundamental identity is A equals U, sigma, V transpose. This allows us to break down a complex transformation into three distinct steps: a rotation, a scaling, and another rotation. It's the mathematical foundation for understanding how data is structured. Matrix U gives us the left singular vectors, which reveal relationships between rows like users in a database. Then, sigma, the diagonal matrix, contains the singular values. These act as weights, telling us which features are most important and which are just noise. Finally, V transpose provides the right singular vectors, capturing patterns across the columns. By keeping only the largest singular values in sigma, we can compress the entire matrix with minimal loss of information. This is why SVD is so powerful in AI. It's the engine behind PCA for dimensionality reduction. It allows us to compress high-resolution images, and it's even how the Netflix prize winners built recommendation systems to predict your movie tastes. It finds the latent or hidden features that aren't immediately visible. Having explored SVD on page 11, we've mastered 2D grids. But in modern deep learning, data often breaks out of the flat plane. Let's step into the multi-dimensional world of tensors, which serves as the backbone for almost every AI model today. We start by generalizing what we already know. A scalar is 0D, just a magnitude. A vector is 1D, and the matrices we've been calculating are 2D. Tensor is simply the mathematical term for an n-dimensional array that encompasses all of these. Take a standard RGB image as an example. It isn't just height and width. It has 3 layers of color: red, green, and blue. This makes it a 3D tensor. When we perform operations, we aren't just moving across a grid, but through the depth of these color channels. It scales even further. If we add a time dimension, like a sequence of frames in a video, we hit 4D. And when we train models using batches of multiple videos simultaneously, we are manipulating 5D tensors. The logic of linear algebra we've studied remains the same, just across more axes. This is exactly why frameworks like TensorFlow and PyTorch are named the way they are. They are designed to manage the flow of these complex data structures through neural networks efficiently. Understanding this hierarchy is key to our upcoming project. Now that we've explored the multidimensional world of tensors, it's time to bring everything together for our final capstone project. As we covered on page 10, singular value decomposition is a powerful tool for finding the most important features in data. In this activity, you'll apply SVD to compress an image by keeping only the top, K, singular values, balancing file size with visual quality. Dr. Eris and Maya are here to guide the technical implementation, while Sophie and Leo will be diving into the mathematical logic and practical results alongside you. Choose your role, and let's see how much we can compress these images without losing clarity. This project marks the conclusion of our session. You've done an incredible job navigating from basic vectors to complex dimensionality reduction. Let's finish strong.